For our design of the 2012 Big Beam Contest, we strove for three things. 1. To use an economical amount of pretension steel. 2. To design for failure and flexure rather than in shear. And 3. To keep the overall design simple. The project involved an 18-foot-long beam with a span of 16 feet, subjected to 2 unfactored 10-kip point loads and 2 additional factored 16-kip point loads, both of which were applied 6 feet inwards from both supports. The overall judgment criteria for this project included 4 parameters for the design of the big beam. 1. The design had to be accurate. 2. It had to be inexpensive. 3. It had to be light in weight. And 4. It had to maximize deflection. In addition to this, the design report had to provide the most accurate calculations for the actual structural behavior of the big beam, had to have quality writing, and had to be practical, innovative, and conform to the guidelines set forth by the design committee. For our design, the following values were given or deduced from other given values for the pre-stressing strands: elastic moduli, area, ultimate stress, yielding stress of the strands, and jacking stress. For the concrete, initial compressive stress, concrete compressive stress, unit weight, and the moduli of rupture were also tabulated. Furthermore, yield stress for A706 steel, the elastic moduli of concrete used, and the initial elastic moduli were also calculated. A reduction factor for pre-stressing losses was specified at a 5% reduction. In addition to the given and found values using ACI section 1842, stress limits were calculated for the tensile and compressive stresses at transfer, the compression stress at the application of the superimposed dead load, and the compression tensile stresses at service. After the allowable limits were found for member stresses, the beam geometry was then optimized using Microsoft Excel. After analyzing 2 other geometric configurations, we chose to optimize the structural design for an asymmetric I-section, with the top flange being wider than the bottom flange. Our final design included a section height of 17 inches, a top flange width of 8 inches, a bottom flange width of 6 inches, and a web thickness of 3.5 inches. Additionally, the height of our top flange was 3 inches, and the height of our bottom flange was 4 inches. Using these perimeter values, we then calculated the area and inertia of concrete to be 83 square inches and 2.53 times 10 to the third inches to the fourth, respectively. By dividing the inertia by the area and taking the square root, we found the radius of gyration to be approximately 5.52 inches. Lastly, the sectional moduli were calculated at 310.63 cubic inches in the tension fiber and 285.69 cubic inches in the compression fiber. The demands on the beam included a self-weight of 85.22 pounds per foot, an induced moment of 2.73 kip feet due to self-weight, and an additional induced moment of 60 kip feet due to the live load. Next, we analyzed the required sectional moduli for the different stages in loading. To do this, we added the moments applicable for each stage and divided the summed moments by the allowable stress limits, some of which were multiplied by the reduction factor of 0.95. After we were assured that these values were less than the design sectional moduli values, we then took the latter values and with them determined the overall stress in the concrete. By multiplying this value by the cross-sectional area, we then determined the initial pre-stressing load on the design section. Once the initial pre-stressing load was found, we then determined a required eccentricity of 6.8 inches for the section. Because we chose half-inch special low relaxation grade 270 pre-stressing strands, our yielding and ultimate stresses for the pre-stress section were 249.5 and 280 KSI respectively. According to ACI section 18.5.1, these values were then multiplied by factors of 0.94 and 0.8. A minimum stress of 224.07 KSI was then yielded, which governed the amount of pre-stressing strands needed. Although this value was 3.84, which indicated that 4 bars would be required, we selected only 2 pre-tension bars and decided to compensate for the required remainder by designing additional longitudinal reinforcement in the compression zone. This gave us an early value of 0.34 square inches for pre-stressing steel in the tensile portion of the big beam. Our pre-stressing losses were as follows. 1. We lost 2.29 KSI of stress due to relaxation at the transfer. 2. We gained an additional 11.91 KSI due to elastic shortening. 3. We lost a total of 2.7 KSI due to relaxation at the time of testing. 4, we lost 2.39 KSI due to shrinkage, and 5, we gained 6.02 KSI due to creep at the time of testing. In summation, we lost just under 185 KSI of stress effectively. Our reduction factor decreased by 1/100%, and our effective load resulted in a total of just over 62 kips. After calculating our losses, we then checked the ACI allowable stress requirements on the final section. For the transfer stresses at the support and midspan only, our initial transfer stress at the support exceeded the allowable limit. For service loads, all final stress checks were less than allowable limits. Once these checks were made, after calculating the depth from the topmost fiber to the center of gravity of the pre-stressed section, we then used strain compatibility to determine the nominal bending capacity of the beam. This included a two-step process of 1, first determining the strain due to pre-stressing, and 2, then calculating the strain due to decompression. After these two strain values were found, a stress-strain curve for the pre-stressing strands could then be plotted. Instead of using ACI section 18.3, 3 iterations were then made to determine the force of pre-stressing in the section. In the first iteration, it was assumed the pre-stressing force was exactly 200 KSI. Using the depth of the equivalent compression block, and then using strain compatibility, a new pre-stressing force of 266.62 KSI was then found. Using this newer value of force, one more reiteration showed the pre-stressing force to be approximately 3 KSI less than the second iteration, and a third and final reiteration verified this to be true, given that the change from reiteration 2 to reiteration 3 was minimal. Using this found value of 263.8 KSI, we then calculated the nominal moment capacity at 104.66 kip feet. Using this nominal moment, we then determined the corresponding factored live load occurring throughout the beam. Because this live load was greater than the 32 kips of force and less than the 39 kips of force specified, our design section was okay, per the specified rules of the contest. Using a strength reduction factor of 0.9, we then found the required moment capacity of the beam was about 99.27 kip feet. After calculating the cracking moment at 65.74 kip feet, we then used simple statics to determine that the live load necessary to crack the beam was approximately 21.9 kips of force. Having only 20 kips of force applied in total, our beam would hold up to the given loads without cracking. Because the diameter of the half-inch special strands was 0.522 square inches, the transfer and development lengths of the beam were calculated at 2.68 feet and 6.12 feet respectively. Because the development length was less than the distance of point load application, 7 feet from the end of the beam, this was an acceptable distance for development. To design the beam for shear, we had to calculate both the shear demand and capacity of the section according to ACI Chapter 11. Because the effective pre-stressing force was less than 40% of the ultimate pre-stressing force, according to ACI, we were allowed to calculate both according to the simplified method. With the simplified method and plotting the values of moment and shear over the length of the beam, we found the minimum and maximum values for shear were 9.27 kips of force and 23.17 kips of force, respectively. By using ACI equation 11.5, we projected the curvilinear trajectory of the shear force with respect to the distance from the support. After graphing both shear demand and resistance, we then calculated the necessary shear reinforcement spacing. We determined that the maximum spacing for reinforcement was 12.75 inches. Based on the plot we formed, we determined that implementing number 3 bars at a spacing of 8 inches for the 6 feet from the support until the point of application would be acceptable. Due to the lower tensile stress capacity of the beam at the support of transfer, we needed to provide mild steel reinforcement in the top flange. Running one number 3 bar along the length of the top flange in the middle solved this problem. In addition to providing tensile strength, this reinforcement was also used to support the shear reinforcements. The total length of the bar ran the full length of the beam and weighed in at 6.77 pounds. By including the additional steel reinforcement and the stirrups along the length of the beam, we were able to determine how expensive the beam would be. Our final cost for the materials used in the construction of the beam totaled in at $58.63. Lastly, we determined the governing deflections per ACI by finding the strains at the topmost and bottommost fibers in the midspan of the beam. We calculated these deflections at 4 different points in time. 1, the initial loading, 2, the placement of service loads, 3, the cracking stage, and 4, when the nominal load would be reached. Plotting these values over the length of the beam, we developed a formula for determining the curvature of the beam for when the deflections occurred. Our final calculation for calculating the total deflection at the midspan was made by integrating the plot over half the length of the span. This gave us an overall deflection of 3.04 inches. The actual fabrication of the beam took place in November of 2011 at Northeast Prestressed Products. The mix of concrete was selected by Northeast Prestressed Products, and every member involved in the competition participated in the setting of pretension and reinforcement steel. The eventual testing of the beam occurred at Fritz Lab on the campus of Lehigh University on the 1st of December 2011.